Dr. Hansen, why do we breathe? To answer that question, I want you to do a quick demonstration. Go ahead and take in a deep breath, and now please hold it for the next hour. Yes, it turns out that breathing is pretty important, and it also turns out that what drives life is oxidation reactions. Whereas oxygen is absolutely critical to all life, you can't live even a few minutes without it, and at the same time, oxygen slowly kills us by forming free radicals, which contribute to aging and to chronic diseases such as heart disease, diabetes, metabolic syndrome, strokes, immune dysfunction. Yes, oxygen is a real Jekyll and Hyde. It is important to know the difference between Jekyll and Hyde, between good and evil. And understanding the role of oxygen in health and in disease processes is greatly simplified through an understanding of electronegativity. Oxygen is the most electronegative atom in life, and accordingly, the electronegative role of oxygen contributes to health by making it the ultimate electron acceptor in the electron transport chain. That means that oxygen is absolutely essential to the production of 95% of the ATP in your body. As electrons fall down the electron transport chain, they need a down direction to fall in. They need a deep energy well, and that is the electronegativity of molecular oxygen. When an electron falls to that extremely electronegative molecule, oxygen accepts those electrons, pulls in some protons, and becomes water. In fact, water is so low in energy that we have oceans full of the stuff. Electrons need to fall from their high energy to the deep well in order to turn the wheels that power the production of ATP. Alternatively, the extreme electronegativity of oxygen makes it evil because it can bump into the essential iron atoms throughout our body and steal electrons to form aggressive free radicals that can destroy our proteins, nucleic acids, and lipids. Yes, the beneficial and harmful effects of oxygen are at the center of many of life's processes and are at the center of an awful lot of diseases. Let's look at an example of good oxygen versus its evil twin, free radicals, superoxide anion. It turns out that many Americans take antioxidant dietary supplements. In fact, back in the 90s, they were taking mega doses of these antioxidants. Why did they do that? What did they think would be the health benefit? And by what mechanism? Please answer. Well, if you want to know what antioxidants do, you first look at the name. Antioxidant. It pretty much tells you it works against oxygen. Now, in particular, they tend to work against oxidative damage, because when oxygen can grab a lone electron, it becomes a free radical and it goes around destroying things. Antioxidants tend to have an extra free electron, and when they bump into a free radical oxygen, they donate a second electron to the free radical, so it now has a pair of electrons, and then that free radical can often be converted into water. So they are antioxidants. They prevent oxidative damage. Now, the next question is, when do you have more free radicals in your body? When you're sitting around relaxing at home, or when you're at the gym working out? Please answer. Well, when you're at the gym, you need to breathe more heavily because you need to burn more oxygen to power your muscles. Whenever you have extra oxygen in your body, whenever you're burning more oxygen, a side product will be free radicals. Roughly, for every 100 oxygen molecules you burn to make ATP, one of them will get converted to a free radical. So in the gym, you make more free radicals. So it might seem logical to take the mega dose of antioxidants before you work out, right? Unfortunately, it turns out that taking mega doses of antioxidants before working out
eliminates the benefit of exercise.
Why's that? Working out at the gym dramatically increases the concentration of free radicals in your blood. Why's that? Exercise requires an increase in metabolism, and a byproduct of metabolism is free radicals. And you're saying, wait a minute, exercise is supposed to be healthy? Well, it turns out that free radicals are signaling molecules, and when you have a lot of them, they signal to your body that you need to build up your antioxidant defense. So accordingly, when you exercise, you want free radicals to increase. For that matter, your immune system signals through free radicals. Free radicals at low concentration are good, and their buildup during exercise are good because the net effect is over time you have a lower level of free radicals and a higher level of antioxidant defenses. Therefore, many Americans taking megadoses of antioxidants are damaging themselves, they're interfering with their free radical signaling molecules, their immune systems, they're getting an increase in the number of strokes, they're interfering with the benefit of exercise. Too much of a good thing is bad. Free radicals, antioxidants, metabolism, aging, brain damage, strokes, birth defects. A lot easier to understand and remember if to begin with you understand the concepts of electronegativity, electropositivity, oxidation, reduction, molecular energy, and how all that relates to these central coenzymes as well as other chemistry going on in your body. Let's begin with a very simple but powerful way of thinking of energy. What fuel is being burned? And for that matter, what does the word burn mean? Please pause and answer now. This will underlie everything we're talking about today. The fuel, of course, is wood, which is largely made of what fiber? How about that polymer of glucose, cellulose, the most prevalent molecule on the planet? And the cellulose form of this polymer is so straight that it can pack together extremely tightly to make the redwood forests. Now, what exactly is the reaction? Please pause and answer. This is critical to the whole talk. Well, everyone refers to burning as a oxidation. That is, the oxygen in the air is going to combine with the glucose in the wood to form carbon dioxide and water. And of course, you do know this cold because you know if you block the oxygen supply, the fire will go out. For example, if you put a glass over a burning candle, the oxygen inside the glass will slowly be used up and the fire will die out. In going from glucose and molecular oxygen to carbon dioxide and water, did the chemical energy go up or down? Please pause and answer. Again, this is at the basis of energy and at the basis of oxidation and reduction reactions. You know intrinsically that oxidation reactions go down in energy because look what is released, heat and light. Heat and light are both forms of energy, and when fuel molecules that have carbon and hydrogen atoms in them combine with oxygen, energy is released, and for that matter, the equation here shows it. We have two molecules on the left, two different molecules on the right, plus the energy that's released, the heat and the light. Now, interestingly, this exact same reaction takes place within your body. You constantly are taking sugar and combining it with oxygen, not directly, but through a bunch of intermediate steps. And instead of completely releasing all the energy as heat and light, you are able to harvest about half of that energy in the form of high energy coenzymes such as ATP and NADH to drive life. So it turns out that oxidation and reduction reactions are central to life. We want to understand how you're able to get this energy. And I'll begin by defining oxidation and reduction. The simplest and most powerful definition of an oxidation reaction is that if you oxidize a compound, you simply form a bond to oxygen. To be a little more precise, a more general term is to oxidize a compound means to form a bond with an electronegative atom, and oxygen is one of the most electronegative atoms. The opposite of an oxidation reaction is a reduction reaction. In this case, to reduce a compound means to form a bond with carbon or hydrogen or similarly electropositive atoms. Right now, let's look at the atoms most central to life: carbon, hydrogen, and oxygen. Please number each of these compounds in order of increasing energy, and number each of these compounds in order of increasing level of oxidation. It is absolutely in your interest to pause the video and do that, but I'm going to move on. One of the most basic learning objectives is the relationship between level of oxidation and level of energy. There is always a correlation. Now, the easiest thing to see when you're looking at molecules is the level of oxidation. Which of these is most oxidized and which is least? Well, the more bonds to oxygen, the more oxidized. Methane has no bonds to oxygen. It is the least oxidized. 1 bond, 2 bonds, 3 bonds, and here we have 4 bonds of oxygen to carbon. Carbon dioxide is as oxidized as carbon can get. Now, what is the relationship to energy? Whenever you look at this type of a figure, say, okay, this is a fuel. What can be burned? Well, carbon dioxide is the end product of a fuel. It's the waste product. No energy at all, because all of the high energy electrons, which are in orbitals between carbon and hydrogen, or similar fuse between carbon and carbon, have fallen to molecular oxygen, so that you now have 1 bond to oxygen, 2, 3, and 4, completely oxidized, useless, very low in energy. What's high in energy are carbon to hydrogen bond. Those are the electrons which can be used. So anytime you look at a compound, see how many high energy apolar bonds there are. Before I move on, I want to make a technical point. Very often in undergraduate chemistry, there's a reference to bond energy, where the stronger the bond is, the more energy. In biochemistry, we almost always look at it from the opposite perspective. So very often as undergraduates in freshman chemistry, they would talk about, oh, it takes a lot of energy to break a bond, therefore that must be a high energy bond. By high energy, they mean it takes a lot of energy to break it. From our standpoint, we're looking at carbon dioxide and saying, hey, we have to put a lot of energy into there to free those electrons up. Therefore, this is low energy. And again, to reiterate, a low energy bond biochemically means a bond that electrons will fall into, a bond that you have to put energy to pull the electrons out. So if anyone has any trouble with the different perspective, how almost all biochemists refer to bond energy, please come and talk with me about it. It'll be very easy to clear up. So again, to us, a low energy bond is a bond in which electrons would fall into it, and it will take energy to pull it back up to a higher energy bond. And now I want to also look at this in terms of the atomic orbitals. So for example, in methane, the carbon and hydrogen are equally electropositive. They don't care much about electrons, so they're pretty much in covalent bonds, evenly resonating around. When you burn methane to make methanol, then some of the high energy electrons in the orbitals linking a carbon and hydrogen have now fallen down to the oxygen atom, releasing some energy. As you burn it more to form a double bond, formaldehyde, now even more electrons have fallen from carbon-hydrogen high energy orbitals to low energy orbitals, largely around the oxygen atom, but linking it to the carbon. As you burn it even more, as you oxidize it more, it goes more down in energy, more light and heat is released, and now you have formic acid, where Now again, more of these electrons have fallen down on top of the oxygens, and so the carbon-hydrogen bond has even less electrons than usual. And finally, we finish the thing off, burn it all the way to carbon dioxide, and now these electrons are trapped in extremely low energy orbitals around the oxygen, not so much around the carbon. And if we're going to want to run these reactions in reverse, we're going to have to put some energy in there to lift the electrons out of those orbitals around the extremely electronegative oxygen atoms. Before I finish with this slide, there's one more important point I'd like to make. You will find in chemistry that having more than one way of seeing things often can strengthen your overall understanding and help you solve problems. The point I'm trying to make is that an oxidation can be defined as making a bond to oxygen. In life, it also can very often be described as breaking a bond to hydrogen, because so often when you form a bond to oxygen, you're losing a bond to hydrogen. Likewise, we can say that reducing a compound is forming a bond to hydrogen or carbon. However, that is often equivalent to saying a reduction means to break a bond to oxygen. In being able to look at these oxidation and reduction reactions from both perspectives, this will often help you in remembering how metabolism works. One more important point considering oxidation and reduction, you absolutely should be able to look at related atoms such as methane, methanol, formaldehyde, formic acid, and carbon dioxide, where there's only a single carbon and it's bonded either to hydrogen atoms or oxygen atoms. Easy to see oxidation level and reduction levels and energy levels. What if there's a different number of carbon atoms?
For example, where in this figure would you put ethane in terms of energy and in terms of overall oxidation or reduction level? Please pause and answer.
Well, first of all, let's say we're burning it. You could burn methane to make carbon dioxide and water, and you could burn ethane to make carbon dioxide and water, and you'd get about twice as much energy from the ethane, because you have twice as many electrons in high energy bonds in ethane as you do in methane. So ethane definitely has more energy. The more carbon-hydrogen bonds, the higher the level of energy. And what about the oxidation reduction level? Ethane would be considered more reduced, less oxidized than methane because you have more reduced bonds, more high energy electrons to be used. Now, to apply this concept to some other important biological molecules, we can look at glycerol, glyceraldehyde, glycerate, and we can look at the coenzymes. Can you organize glycerol, glyceraldehyde, glycerate in order of increasing oxidation, increasing energy, NADH, NAD+, FADH2, FAD, and even glucose and ribose? It is in your interest to answer that question, but I do need to move on. So glycerol gets oxidized by forming a aldehyde group, which gets oxidized to form glycerate. So increasing oxidation means to go down in energy. NADH loses a hydride ion to become NAD+, so that goes down in energy. FADH2 loses hydrogen atoms to become FAD, again getting oxidized and going down in energy. Glucose, compared to ribose, is going to have more energy because they have identical carbohydrate composition, but glucose has one more carbon atom. In light of the fact that glucose is 50% of all dietary energy on the planet, and since it's so central to glucose lysis, glycolysis, sugar metabolism, diabetes, let's take a closer look at this important fuel molecule. In particular, if you look at glucose, which bonds are polar, low energy, which bonds are apolar, high energy, and in particular, we can look at each type, carbon-carbon, carbon-hydrogen, carbon-oxygen, hydrogen-oxygen, and oxygen-oxygen if you're looking at the molecular oxygen, which is used to burn the glucose. Please go ahead and give some idea of energetics and of electronegativity. but I need to move on. We know that carbon-to-carbon bonds have high-energy electrons because carbon doesn't care that much for the electrons and they can fall to oxygen. Likewise, carbon-hydrogen bonds, and I've colored all these apolar, high-energy bonds in blue. In contrast, in a carbon-oxygen bond, the electrons are being pulled from the carbon atom onto the electronegative oxygen, so these are fairly low-energy bonds. Since glucose is C6H12O6, every carbon has been about a quarter oxidized. This carbon, for example, has one bond to hydrogen, two bond to carbon atoms, and one of its bonds to a hydroxyl. Once we burn glucose, we'll have water and carbon dioxide. Here, the electrons holding the hydrogen to the carbon have now fallen and hold the hydrogen to oxygen. Those electrons have gone down in energy, they've fallen toward the oxygen nucleus, and there's a huge polarity to the water molecule. Likewise, the electrons in the bonds holding carbon atoms to carbon atoms have also fallen to oxygen atoms, such that these bonds are also highly polarized, with most of the electron density being over the two oxygen atoms and a little bit over the carbon. It makes really good sense that we have high energy electrons in carbon-to-carbon and carbon-hydrogen bonds, these apolar bonds. Sometimes what people find confusing is molecular oxygen because they go, oxygen, oh, that's like in water. But there's a big difference. The oxygen atom in water is profoundly different from the oxygen atom in molecular oxygen. The oxygen atom in water is extremely electronegative, whereas the hydrogen is extremely electropositive, which means extreme polarity. In molecular oxygen, both atoms are oxygen and are equally extremely electronegative, which makes this profoundly apolar. Accordingly, most of the oxygen in your body is not floating around in the cytosol, it's floating around in your membranes, and of course some is bound to hemoglobin. So molecular oxygen is similar to sugars in that the oxygen-oxygen bonds are apolar, just as the carbon-to-carbon bonds are apolar. They're different in that the molecular oxygen has electrons it will not release, and it will steal more electrons from the carbon-to-carbon bonds, whereas the carbon-to-carbon bonds will readily lose electrons. And at this point you might be saying, okay, Dr. Hansen, so yes, the sugar is being burned, the high-energy electrons in apolar high-energy orbitals are falling into the oxygen to make water and carbon dioxide. But how much energy is there in the falling of an electron into an oxygen molecule? In fact, you're correct, that's not a lot of energy in one molecular reaction. But there's an awful lot of atoms in these. This is how human beings are built from our diet, largely from the energy in sugars, in glucose, and in fats. Furthermore, if we want to look at hydrogen-to-hydrogen bonds, we could consider the story of the Hindenburg dirigible, which was full of molecular hydrogen H2.
It's practically standing still now. They've dropped ropes out of the nose of the ship, and has been taken a hold of down on the field by a number of men. The back motors of the ship are just holding it just enough to keep it. It bursts into flames. Wait, get it started. It's crashing terrible. Oh my, get out of the way, please. It's bursting into flames, and it's falling on the morning baths, and all the folks between us. This is terrible. This is one of the worst catastrophes in the world. Oh, it's 400 or 500 feet into the sky. It's a terrific crash, ladies and gentlemen. The smoke and the flames now, and the flame is crashing to the ground, not quite to the mooring mast. Oh, the humanity.
Yes, it turns out you can get an amazing amount of energy by having electrons fall from electropositive molecules to electronegative molecules in order to make low-energy polar molecules. To be clear, if there are only 2 hydrogen molecules and 1 oxygen molecule to make 2 water molecules, that's a very small amount of energy. But atoms and molecules are extremely small,
and there are a huge number of them even in a small space, such that filling a dirigible with hydrogen does leave the potential for a disaster. And I guess that's why now they fill them with a very light, inert gas, helium. Molecular hydrogen and molecular oxygen are quite inert. The electrons in these orbitals are quite stable, and it would take quite a bit of energy to perturb them to allow the reaction to occur. Usually what would happen is a spark, such as happens in your automobile engine. A spark could then disrupt some of the atomic bonds, allow the electrons to fall to molecular oxygen. As soon as they do that, they are going to release light and heat, just like a fire. That heat and light again can perturb more bonds, and you have a massive explosion as you form water. And just as you can get a lot of energy from molecular hydrogen, humans get a lot of energy from molecular sugar. Oxidizing 1 mole of sugar will release 686 kilocalories of energy. In a campfire, that energy will be released in the form of heat and light. In the human body, that reaction occurs in multiple steps, in which at many steps, energy is harvested in the form of high energy bonds, ultimately in the form of ATP. To beat this dead horse even further, I want to make an analogy between a hydroelectric dam and the electron transport chain. In the electron transport chain, electrons fall from high energy orbitals and fuels all the way down to a low energy reservoir, the extremely electronegative molecular oxygen, in order to form water. And as the electrons fall, they drive wheels which produce ATP. In the hydroelectric dam, there's a high energy well that water falls from under the force of gravity. It spins wheels to produce electricity and end up in the low energy well. And so the question is, why do we need that low energy well? We have high energy, isn't that enough? Well, if we don't have oxygen to accept those electrons, or if we don't have a low energy reservoir, then the water can't fall and turn the wheels. You have to have a high energy reservoir and a low energy well to fall into. In fact, I think it's obvious that the low energy well is as important as the high energy well. You need both. And that's why we have to have oxygen. That is why we breathe. And whether the high energy fuel molecule is carbohydrates or whether it's hydrocarbons, those high energy electrons will fall from that fuel molecule down to the low energy orbitals in molecular oxygen in order to make water and carbon dioxide. Inclusion, your metabolism is being driven by oxidation reduction reactions. And as we look at metabolism over the next couple weeks, any reaction you look at, the first thing you should say is, oh, which way are the electrons going? Is this going up in energy? Is this going down in energy? Oxygen is the ultimate electron sink for life. This is why we need to breathe, and it's why we need our cardiovascular system to pump oxygen throughout our body. And of course, that's why cardiovascular disease is so life-threatening. Nevertheless, oxygen has a dark side, and these reactive oxygen species are not only beneficial as cellular signaling molecules, but they're also harmful in excess and over long periods of time. If you have any questions about this, what I think is just an amazing story about low and high energy wells, don't hesitate to phone me, email me, text me, and I'll see you in class.